Hello, friends. Today I just want to go through proximal policy optimization. I'll be honest here, I don't know much about proximal policy optimization. I just know that it's one of those reinforcement algorithms that's being used in a ChatGPT development. Um, it's one of those reinforcement algorithms. I've barely read something about it, but today I'll just browse through some articles on Huggingface and try to see if can learn about proximal policy optimization. Okay, let's see. I think this was the link that I was going through. Okay, we have this. So it seems that it's part of deep reinforcement learning class with Hugging Face. It's part of a lecture series. I'll try to understand this from this article. If I don't get it, I think I'll go back and try to maybe look into other resources. First, let's look at this one. So what does it say? We learned about advantage, active critic, a hybrid architecture combining value-based and policy-based methods to help to stabilize the training by reducing the variance with an actor controls how our agent behaves. Okay, that's kind of like the policy-based method where the agents try to decide what action is the best given a state. I think that's what the policy-based methods are about. So the actor agent, the actor part of advantage actor critic controls how our agent behaves, whereas the critic part of A to C, it measures how good the action taken is. So it's kind of like, I think there are two parts to this. One part is about making decisions, and the other part is about evaluating how good that decision is. So we can see that the agent should try to take steps and should try to learn, and the critic should try to kind of like tell which of those actions are better. Now, at a very high level, the actor can try one of those infinite possible moves in any environment, which is kind of like an unconstrained environment. Then the critic can still tell that, but the learning rate, if that is not good for the actor would still make a lot of moves uh, that might not help in its evolution. On the other hand, the actor, if it learns quickly and makes those moves, but then the critic is evaluating only those top 5 moves and then is able to evaluate well. And if the actor can learn quickly, the actor can evolve into a good agent that can make the best out of a given environment. Right? So that looks like a method where the agent tries to take some actions, uh, possibly the ones that would reward it highly, and critic is the critic basically tells it like, okay, which of those actions that it has taken are good or bad. So the actor should make good actions and the critic should be able to discern or like kind of tell between two actions how good that action would be compared to a second best action or the action that was not taken, right, in a given environment. So let's see, let's go forward. So we'll learn about proximal policy optimization and architecture. Okay, it's an architecture, it's not an algorithm. I thought it was an algorithm. Maybe, I don't know what's the difference, but an architecture that improves our agents training ability or stability, sorry, stability by avoiding too large policy updates. So it talks more about training stability, not about the actual algorithm. So this kind of like makes me think about it. Is this like a new algorithm altogether, or it's got more to do with reducing those instabilities in the training? And say, let's think of it like this. You have gradient descent algorithm. At the heart of it, you're just trying to find out where would be the steepest direction for reducing the error, that basically like the opposite of your gradient in any given point. Then you can make a move depending on your own learning rate, like, right? So if you make you learn, if you keep your learning rate very high, there's a possibility of you jumping all over the space and missing those uh, bottoms, or like what do you say, minimas, right? So there are like many algorithmic improvements on how the learning rate should evolve. They talk about making those incremental small updates, so that you're just traversing in the direction of the gradient descent, but at the same time you're not jumping too far ahead that uh, you're going in some other space which uh, will not be helpful for you, right? So this looks sort of like that. That's this architecture already, the A to C architecture, but now PPO is trying to kind of make that algorithm stable. So I believe this is more of an architecture. I also heard about something called DPO, direct preference optimization. Let's see if we'll try to go through that one as well in the next few like few recordings, depending on how this goes, of course. Okay. To do that, we use a ratio that will indicate the difference between our current policy and the old policy, and clip this ratio from a specific range. So it looks like, let's say you're playing chess. Maybe you found out like your agent is making moves. It is found out that moving queen in the initial few moves is not good, right? But then it has taken this decision that to never move the queen, right? You don't want such action. Like maybe it's good to not move the queen until move 5. But if it learns to not move the queen until move 30, right? You're basically reducing your benefits. Like you're not exploring full strength of your position, right? So kind of like that, like you want to only make those changes, updates to a policy incrementally, right? uh how might this help, right? Think of it like, I think for me, right, reinforcement algorithms of the current day are more about learning uh the probabilities of go like it's more about like, okay, in this position of chess, if you make a knight move 40% of the time, or a bishop move 20% of the time, or a queen move 10% of the time, so these are kind of good moves, right? Depending on your position, like if you give me a snapshot of a chess position, there are like different paths I can explore, and that will give me like uh, a good probability on a knight, and then a smaller probability on a bishop, or like that. So it's basically like you're trying to update those probabilities, right? Just like you're trying to learn the representation of what's the best move, what's the most probabilistically best move to take there, right? Um, so that's the kind of thing. And I think because of such what do you say, representation learning, since we are kind of updating those probabilities, we don't want to update them like drastically depending on what we have seen in the recent example, right? Because we're going to see like infinite examples, and we're going to build our probability mass based on the entire input space. So we only want those updates to be very incremental, but we'll correct this if this is not the case. This is my intuition right now. And remember, I don't know anything about it, so all I'm trying to do is try to understand this intuitively. Okay. Doing this will ensure that our policy update will not be too large and the training more stable. Yeah, kind of like that. Like, so it's like you don't want to change your algorithm too much. You kind of trust it. You don't want it to change depending on only one example, right? Uh, you're getting some loss with the recently exposed example, but only change it ever so slightly, because if you have to change a lot with in relation to this example, think of this like this. You'll see more examples of this position or this state of the environment often, depending on how frequent this is within that environment space, right? So if you only make incremental changes, the probability of your agent getting exposed to those states will itself make sure that your training algorithm or your exploration phase will cover all sorts of updates, right? So that's the kind of thing. And I think epsilon here, right? Like you can go wrong. Like when you choose something like an epsilon, that's gonna be like, okay, for each problem there's gonna be one epsilon, and I think there has to, it's more like a hyper parameter. uh you have to do an experiment for your own space, own class of oil algorithms, and find out what your epsilon would be, because an epsilon of like an update which might be deemed as a small update in a go game, go agent, might not be small one when you do it for chess agent, right? And it might be very different for reinforcement learning like RLHF in ChatGPT. So it depends very much on the problem that you're exploring. Okay. Then after three, we'll code a PPO architecture from scratch using PyTorch and Bulletproof for implementation with Cardpole. Okay, I've not gone through these examples. I would love to learn them. Okay, but what's there here? Okay, we don't have much to think about here. Sounds exciting. Yeah, it's really exciting. Let's get started. The intuition behind PPO. Let's see the agenda here. Here's something like introducing clipped surrogate objective. Then there is policy objective function, the ratio function, the unclipped part, the clip part, and then visualizing the clip part. I think there are few cases to consider. What happens when the ratio, when the updates are big? What happens when the ratio is within the range? What happens when the ratio is less than the range? Right? And score the PPO agent. Let's go. Okay, the idea with proximal policy optimization. I think sounds fancy, but again, they put the name like very intuitively. It's policy optimization, and you're doing it just exploring a proximal space, I guess. Is that we want to improve the training stability of the policy by limiting the change you make to the policy at each training epoch. As simple as it can get. You train to update your policy, right? Your agent has a policy, and at in the first stages, it's completely random. It doesn't have any idea what to do given any state. It does something, it learns from that. It creates a policy of sorts, and over epochs, you update these policies, right? The policy, and after every epoch, you make only a small change, I guess. We want to avoid having two large policy updates. Why do we want to avoid two large policy updates? It looks fairly, I think, intuitive to me. Um, we know empirically that smaller policy updates during training are more likely to converge to an optimal solution. Yeah, that's true because you're moving ever so slightly in the direction of gradient. You're not making those bold jumps that would take you into some other space that was not guiding you to, right? Um, that's a catch though, like similar to a gradient descent algorithm, like having a smaller learning rate will make you train forever in spaces where like your learning rate is small, right? Like if you're learning, then let's go to the second option, second reason here. Too big step in a policy update can result in falling off the cliff, getting a bad policy and having a long time or even no possibility to recover. That's possible, right? Like the same thing, like it's the same as jumping here and there within that space of uh, in gradient descent algorithms. I'm not sure how you would jump off the cliff completely. You would maybe go to a suboptimal policy. I would think of that, but I don't think you would go as far off as creating a random policy altogether. I don't think all the spaces are like the ones that are shown here. Um, this seems an exaggeration. You're not going to go fall off, and then you're not going to try to kind of go, because you're always trying to reduce low, and then your spaces are going to be more convex than they are here, right? This looks like some space where there's only a tiny path to optimization. I don't believe in that. Mm, it's more like it's not stable. You might never come to a global minima, or you might miss global minima and go to some local minima, or like instead of most optimal policy, you might go to suboptimal policy, and or you might oscillate between not finding optimal, like optimal policy, and just always oscillating uh, in a space, right? So these kind of issues can happen, but the image here is an exaggeration, I believe. Needs to be updated. Maybe they'll do that. explained by Jonathan Hui. Modified version from Orel. Yeah, but the line they mentioned is, I think, very intuitive. Taking smaller policy updates improves the training stability. I'm not going to go into this article. I believe one article is too much for me. Let's move on. So with PPO, we update the policy conservatively. Yeah, that's been the theme so far. To do so, we need to measure how much the current policy changed compared to the former one using a ratio calculation between the current and former policy. I assume like that. Like, so what are we doing a ratio on, right? So that's important. I think I'm not aware of that. Okay, and that's something we'll check. I think that ratio has to be a ratio of how much the policy has changed. Policy to me is a plan. How can you measure a policy, right? Um, and okay, let me think about it. Right? Policy is a plan, but it's not a plan that you're thinking about like in all states. You're only thinking about the plan or the strategy in the current state, right? So it's something like this, right? Like what's a policy in any algorithm? It's like given a state, what's the action that you have to take? And there's always a probability mass on which action to take. Like if you're learning an agent for chess and that agent, like, okay, the first given a state of, like, say you're on 14th move, you have a board, and the agent thinks that in that position, making a knight move, maybe I'm just saying after possible maybe 3 to 4 knight moves, there's one knight move that's better. It feels like, okay, that's the action that I would like to take that has the most probability for success. That's what it believes. And then there might be some moves for the same knight moving into some other position, and then some other pieces moving into some other positions, right? There might be a sequence of steps ordered, or like a rank of steps ordered by the probability mass for taking that step in that state, right? And I think uh, that's what it means. Like, okay, given the state, what's the probability of taking that action, right? Uh, that should not change too much between two updates, right? Uh, is that for like the entire probability distribution, or is it only like the top action, right? I believe it's only for top action, right? It should not change. It should only, like, I think, vary ever so slightly is what I believe. Okay, let's maybe go through this again and then try to correct it later. We need to measure how much the current policy changed compared to former one using a ratio calculation between the current and former policy. And we clip this ratio in a range 1 minus epsilon to 1 plus epsilon, meaning that we remove the incentive for current policy to go far from the old one. Instead of saying we remove the incentive, we constrain the policy, right? I think that's the best way to say it, right? You're not allowing it to change as much. I'm not trying to be critical on this article. This article is helping me learn, but I think the wording is, instead of removing the incentive, it's a we are constraining it, even if it tries to. That is essentially is about same as removing the incentive. Okay, here we have some math. A little scary. Let's go through it. Introducing the clipped surrogate objective. Recap. The policy objective function. Okay, I've just read this before this recording, but again, this is very new to me, right? Let's remember what is objective to optimize and reinforce. Okay, this is a reinforcement of policy objective function. I'm not sure what LPG of theta is. Theta, I believe, is the parameter space, and uh, ET is at any time step. I guess expectation at any time step. Um, so it's this. Mm, log of pi of theta of AT given ST. Okay, ST is the state at time T. AT is action T in a state T, right? And then pi of theta, pi is the policy. So policy given a network of parameters. Now, what's the expectation of log of probability of taking that action times. Okay, there are two parts to this. One is probability of taking that action in that state, and the other is advantage. If a greater than zero, this action is better than other action possible at that state. Advantage of that action, I believe. It's only for advantage of that action. And there are like different actions possible, like just like we discussed. AT could be moving a knight to one position or bishop to other position, and then there are different probabilities for the model believes will reward it heavily, and models its probability. And there is an actor critic who believes that uh, given this action in this state, this is the advantage of that. This is basically the reward that you can expect. Now, in this state, this is the expected gain of the policy, right? So this essentially captures what are my possible actions in a state, what is the probability of taking those actions, and what's the reward that I can accumulate if I take these actions. I'm doing an expectation sum, right? So this is basically the total expected reward that's captured by the policy. Now, if I make an update, I think that update can be, the reward should not change drastically, right? That's what I would constrain myself on. Like if you made an update and the reward looks completely different, I think then you're making a big policy change, believe. Okay. We only have like 5 minutes, I think. I'll stop soon at where I'll stop here. I think before we go to the clip surrogate function, just we'll stop after the policy objective function. So the idea was that by taking a gradient step ascent on this function, equivalent to taking gradient descent of the negative of this function, we would push our agent to take actions that leads to higher rewards and avoid harmful actions. That's correct. Like essentially, we're trying to maximize its expected rewards in this state. So we make those updates, and uh, eventually we want to update this agent to take those actions, which would lead to the highest reward, right? However, the problem comes from the step size. Too small, the training process was too slow. Too high, there was too much variability in the training. Yeah, this just follows from what we know in gradient descent. Here with PPO, the idea is to constrain our policy update with a new objective function called clip surrogative function. Okay, we'll constrain the policy change in a small range using a clip. I get it. I think like it's this thing, right? Like again, what we discussed, like now it was making a night move, and later it should consider that night move still, but it shouldn't be something like, okay, now I won't make this night move at all. Uh, Make some random like rook move, like which was like a 15th move in that order. Like I would say still like just a small policy like probability update should happen. Like, okay, the probability of taking a night move to some step on the board should go from like maybe 0.45 to 0.43 and not like 0.2, right? So you don't want those big updates because then the reward function, I think, oscillates. I'm not sure how that oscillates so much, but I believe it oscillates, right? Because you change the policy too much, you don't know where you're going. You just want to make those updates ever so slightly, like expose it to more games. So because this is reinforcement algorithm, like you have to expose it to the amount of games that it would see in real life. Like if it played like over a million years, right? It should get exposed to that level of probability of like that level of states. So it'll eventually, if it is supposed to come to point two, if you expose it to those many games, it will eventually come to that point two. Your policy should not directly drive it from 0.45 to point two, right? So that's the idea here. But we'll see how that clipping happens. But we know that the idea is to constrain our policy update with a new objective function called clip surrogate objective function. They'll constrain the policy change in a small range using a clip. Okay, thank you for listening me ramble so far. In the next recording, I'm not sure when that's gonna come. Uh, I'll try to see how that clipping happens. I don't think this algorithm is like that innovative in terms of what it's trying to do. I believe it's more to do with uh, the stabilities, which might be more important for practical engineers. I was not one, so I don't understand the beauty maybe until now, but we'll see. Uh, Thank you. Bye bye.